All right, hello everyone, and welcome back. This will be the part 2 of my Stevenson Lewis repository video, where I show off some of the features and functionality of the code that I have written here. So let's start up the main script again. So I'm going to go in here and hit F5. All right, so you see we are flying and there's some things that pop up. So let me just go to that screen to show what pops up in the command prompt when I start this. So you see that it says it's using a joystick, and it found the joystick and wrote it out, T flight HOTAS 1. And then it shows, it says there's 8 axes, 15 buttons. I don't use all of that, and I specifically designed all of my flight controls for this T-Flight HOTAS 1. So if you have a different joystick, it might work, but there might be some adjustments that you need to make to get it to work exactly the way that you want. So that shouldn't be that hard, and I'll show off that later in the video. But you can also see that it says arrow left for the rudder, arrow right for rudder right, and then T to select the flight control system. And that T stands for trimmer, or the trim tool. So let's go ahead and go back into our Pygame window there and select T. And then this screen should pop up. So it has the flight control system, and it says SAS right now, Selected Stability Augmentation System. And what this is it's two examples, two really early examples in chapter 4 from Stevens and Lewis. The first run is a pitch stability augmentation system. And that is example 4.4-1 in the third edition, which is the edition that I have. It's the one with the sweet space shuttle cover. And then the next one was example 4.4-3, a roll damper / yaw damper design. So with those two implemented, you now have a stability augmentation system in all 3 axes. So we can click that though, and then we can look at what it looks like with that off. So if we click N, which is for none, then we'll have no stability augmentation system whatsoever. And then if I hit apply to that, now we're flying without any augmentation. You could see, whoa, the pitch axis is entirely unstable. So this is something that the F16 and most modern fighter jets actually utilize. It's called relaxed longitudinal stability. And they employ an augmentation system in order to make the pitch axis stable. And so that's what's being done in Stevens and Lewis as well, is that the pitch axis is unstable and it requires that pitch stability augmentation system, pitch SAS, you could say, in order to stabilize that axis. Now there's also a roll damper and a yaw damper. So to show that off, I'll do a quick roll and try to stabilize a little bit here in pitch. Do a quick roll, and you can see that after I do that quick roll, the roll axis, especially the yaw axis, moves quite a bit. To highlight this even more, I could do a rudder input. So I'll go try to stabilize a little bit in pitch, and then left, right, left. And you can see how much the lateral and directional axes move from those inputs. Now, if I go back to the trim tool, so I hit T again, and then we go SAS on, I hit apply. Now when I do a rudder input, it damps out really quickly. There's just a small movement, and then it gets completely damped out. So that is the benefit of having a lateral directional stability augmentation system. It also damps the roll axis too. So when I let go, it's much more stable. Now it does reduce some of the responsiveness, and that is why most fighter jets actually opt for a command augmentation system as opposed to a stability augmentation system, because we can gain that up and get the response that a fighter pilot would need to do very quick and responsive maneuvers. All right, so going back to my repository here and looking at a few of the folders, we have under this scripts folder, examples, flight controls, modeling, PFD, which again was created by Pablo Ramirez Escudero, who really spent a lot of time working on that primary flight display in Pygame. Really enables us to bring this thing to life. So big thanks to him again. And then tools. So I'm going to highlight flight controls to start. And this is where I have written the stability augmentation systems that I just showed. So if I open up this script here, then you can see that I am doing a few things here. So the thing I want to highlight, though, is how I have these elevon, aileron, and rudder controller functions here. And what these do right now is they look at the state of the vehicle. For the elevon controller, we're feeding back alpha and pitch rate. So you can see that it gets the pitch rate, it gets alpha, and then the elevon SAS is just summing a gain, K alpha, times alpha, and then a gain for pitch rate times pitch rate. And then it's going to return that value, and we're going to sum all those together in this update controls from flight controls function here, or flight control system. So elevon is done here. So it gets the elevon SAS, gets the aileron SAS inputs, gets the rudder SAS inputs, and then it changes the control state of the elevon. So this is, we're passing in this structure here by reference, and then it's going to be updating that value. You could also see that for the elevon, we have to care about what the trim is. So we're always adding that to a neutral state that the trim command is going to adjust. So that's a brief overview of how this works. But there's one thing that I want to highlight that shows the utility of actually flying this. And just flying it with a primary flight display totally gives you enough of an understanding to fix what I think is a problem in the Stevens and Lewis example. So this is for the lateral directional stability augmentation system, so the roll damper and yaw damper in example 4.4-3. So you see that aileron controller has a gain of 0.1. And the gains are essentially your design for the augmentation system. We pretty much knew what we wanted to do going into this design. That's usually how it works in flight controls. And then the key detail is what you choose for a gain. So for the aileron controller, we chose a gain of 0.1. Now in Stevens and Lewis, the gain that he uses for that, or that they use for that example, in Stevens and Lewis, the gain they use for that example is 0.4. So let's change this to 0.4 so we can see how that would actually fly in our simulator. So I change that to 0.4, I hit save, and then we can run main.py again and get the PFD up. Now I need to make sure I'm trimmed at the right state. All right, so in example 4.4-3, the airspeed and altitude that they give is 0 feet and 205 feet per second. So we can hit T and trim at that altitude. Now let's start by turning the stability augmentation system off, just so we can get an idea of how the bare airframe performs at this flight condition. All right, and you could see that, so we're at around 120 knots, and it's pretty clear that the roll mode is going to feel really sluggish and have a huge Dutch roll response, very lightly damped. Part of that is just because of how large our angle of attack is. So you get a lot of side slip, and we got too slow. So that was a challenge to fly. But let's try that again with our stability augmentation system. So I exited out, but let's hit F5 and get back in there, and then let's trim out again at 0 feet and 205 feet per second. Okay, we started to speed up a little bit there, and that's mainly because the alpha is so high that the elevator is going to want to instantly respond to that. But let's try to get to that 18.8 degree angle of attack that it says the aircraft is trimmed at. Angle of attack is one of those things that is invariant depending on your flight control system. So it's not going to, as long as you trim for the right angle of attack by using the trim hat, you shouldn't have a problem with, oh my God, so sluggish in roll. You see how sluggish that is. Very challenging to fly. I could put the nose down just a little bit here, get some airspeed back. Yeah, so this is like slow flight. Just trying to stay above the ground. Let's give it some more power. Really high angle of attack. Gonna give it a little too much power, but we're also low on altitude. We're below sea level right now, so that, I guess we'd have to be flying at the Dead Sea or something to be able to maintain that. Or Death Valley, maybe. All right, so yeah, it's a challenge to fly either way. This is a very interesting point to design an augmentation system at, but obviously an aircraft needs to be able to fly at a lot of different conditions. So this is one where the lateral directional mode is really a challenge. So it makes sense to look at this as kind of an extreme case. Now, one thing that I noted is that the roll mode, if we just get a little bit faster, a little bit out of this trim condition, the roll mode is really sluggish. It's really hard to maneuver this thing. And this is supposed to be a fighter jet. It's supposed to be able to do aileron rolls, and it's supposed to be very snappy so that the pilot is able to quickly maneuver and point the nose. So one way that we can improve that is just by decreasing that roll gain. So it won't be quite as stable, but it will be more maneuverable. The two are usually inversely related. So let's go back to flight controls and let's change that gain. All right, so we have this gain of 0.4. Let's change it to 0.1. Hit save. And then let's get back to that same flight condition and see how it performs. All right, so I'm trimmed at that same flight condition here. And if I do a roll input, you'd see that I'm able to acquire that point much faster. And it's less stable. The Dutch roll has much more of an impact in the roll mode or the roll response, but the pilot might be okay with that if what they want is a quicker response in roll. And that may change depending on the phase of flight. So what Stevens and Lewis created might be okay for an aerial refueling task or landing, something where they need a really stable roll axis. But for maneuvering and for dogfighting, maybe a gain of 0.1 is much more appropriate. And another thing that's really cool is that this is pretty much what they do in the Air Force Test Pilot School. They have an F16 that has been modified to be a variable in-flight stability test aircraft. And that's called the Vista. And it's an F16 that they use to demonstrate different flight controls principles so that the Air Force test pilots, or any test pilot that goes to the Air Force test pilot school, is able to get a really good intuitive understanding for seeing these poor handling qualities in an aircraft, actually fly them, and then be able to tell engineers what is wrong with the vehicle response. But of course, if you are a good engineer, then you will know because you took the time to actually look at what the vehicle response looks like and fly it yourself so that you made it easier for the test pilot to now talk to you about what is wrong with the flight control system. So the last thing I wanted to do was just walk through a few of the folders in my repository here. Examples is where I store all of my Jupyter notebooks where I walk through examples in the book. And I hope to be able to add these to flightcontrols.py in the future so that we can test these out in the simulator. The next one is modeling, and that is where I have all of the code that actually runs the sim. So you can see in equations of motion.py that I have all of the code for the F16, and then I even have the code for one of the longitudinal transport models that he has in the book as well. I've already talked about PFD. The other one is tools. So these are some tools that I just create in order to help myself with either control system analysis or trimming the aircraft, anything like that, linearization. I'm going to throw in this tools folder here. So the last thing I want to show is how I do inputs. So if you go to modeling and then real-time sim, we can open that up and you see this function on line 70 here is called update controls from keyboard. And this is the function that I created in order for you to be able to fly it in case you don't have a joystick. So yeah, you can still fly it from the keyboard. It works pretty well. You might want to change a few things if you want it to be a little more responsive, but if you just want to get up and running with it, you don't have a joystick, it'll automatically detect that you don't have one, and then it will default to that setting. And this is the update from joystick. So this is dependent on the joystick that you have, of course. It calls in this joystick package, and then it will get the trim hat for trim, and it will get axes for the aileron inputs, elevator inputs, and the throttle inputs. So if you want to update any of this, this is where you would go. And it should be just as simple as changing the number of the axis to get it to match what you expect, and then it will all work fine. So that's where that lives. All right, so that's going to do it for this video. I hope to be able to add some flight control laws in the future and walk through some of the examples in Stevens and Lewis. And then hopefully I can even go beyond the examples in that book. I really want to work with the altitude bug and the heading bugs that you see on there to do some autopilot work. So that would be a really fun next step for this project. If there's anything else that you want me to see or go over, please just let me know in the comments or let me know on GitHub. And please feel free to collaborate with me. I'm looking forward to seeing improvements to my code. So thank you and hope to see you again soon.